Okay, so yesterday, the problem that we ended on was a discussion of say that you essentially wanted to solve a system of congruences. Um, so start out asking the question, what's a number x such that when I divide by 3, I get a remainder of 2. When I divide that number by 5, I get a remainder of 3. And when I divide that number by 7, I get a remainder of 2. So writing that in congruence language yields this system of congruences. Okay, and so that's what the topic of the Chinese remainder theorem is essentially solving these systems of congruences. And so the theorem that we call the Chinese remainder theorem is going to give us under which hypotheses it's required for such a system to actually have a solution. So we are going to come to understand under some mild hypotheses that we are going to get a solution to this system of congruences. So before I get to that statement, I wanted to just take a crack at this, not theoretically, but just take a particular example of a problem like this. We'll start out with a system of two congruences and try to come up with a method that we might solve this by. So just kind of doing it the brute force way is going to yield a method that essentially proves the Chinese remainder theorem. So to see this, let's consider a different example. So we'll return to this problem a bit later, but let's take a crack at a simpler thing. So suppose we wish to solve the system of congruences x is congruent to 2 mod 3 and x is congruent to 4 mod 5. Okay. So what do we do here? So to do kind of the most straightforward thing, what I do is I start with the congruence that has the largest modulus, so this one. We'll see why in a second we want to start with the largest modulus. It's just gonna, you can start with either one. It's just if you start with the largest modulus, this process is going to be shorter. So starting with the congruence with largest modulus, so that's 5 here. So looking at this congruence, and what I want to do is start listing the positive integers that are congruent to 4 mod 5. Okay, so I'll start with congruence having largest modulus and list positive integers satisfying it. Okay. All right, let me get another sheet of paper and I'll restate those. So my example, so I have the following two congruences. So x is congruent to 2 mod 3, but simultaneously x is congruent to 4 mod 5. Okay. All right. So as I said, start with the congruence with largest modulus. Is just start listing out the integers that are congruent to 4 mod 5. So integers that are congruent to 4 mod 5, well, 4, obviously. Next in the list is 9. And next is 14. I just keep adding copies of 5 here. 19, 24, 29, and so on. Right. Okay. And now what I want to do is rewrite these things mod 3. So I want to consider x mod 3. Okay. Why mod 3? Because my other congruence is mod 3. Okay, so considering these numbers mod 3, 4 mod 3 is 1. 9 mod 3 is 0 because it's divisible by 3. 14 mod 3 is 2. And I stop. Okay. What does this say? So this says that x equals 14 solves this system. Why does it say that? Well, if I'm looking for an x that is congruent to 2 mod 3 and 4 mod 5, well, this first line is me listing out positive integers that are congruent to 4 mod 5. So anything in this first line, any integer in this first line satisfies the right congruence. And then listing out what these things are mod 3, I'm looking for when one of these is equal to 2. Okay, because when one of these is equal to 2, the fact that it belongs in the first line tells me it solves the right congruence. And then it being 2 in the second line tells me it solves the left congruence. Okay. So, because of that, this is my method for finding something that solves both congruences. So, a couple of things to note here. So, one, note. This isn't really something to note because maybe you don't know this yet. So, Chinese remainder theorem says that this is my solution mod 15. Okay, this is going to be my only solution mod 15. We'll see later why this is the case. And second, we could have started with the congruence x is congruent to 2 mod 3, but it would have taken longer. Not much longer, just a couple of entries here. Because we would have had to list out more things. So if I was doing my list here, I got it as the third entry. If I was listing out x is congruent to 2 mod 3, what would that look like? Well, that's 2, and then 5, and then 8, and then 11, and then 14. So I wouldn't have got to 14 until my 5th entry instead of my 3rd entry. Is that the biggest deal in the world? Of course not, but this is the reason why in this process you can optimize this by just starting with the congruence having the largest modulus. Okay, so let's do another example of this where we do 3 congruences instead. Okay, so another example. Let's say we want to consider the congruences x is congruent to 4 mod 5, 5 mod 7, and 3 mod 11. Okay. All right. This process is going to be the same. It's just that I have 3 things, and so you're going to see how I fold these 3 things into first 2 congruences, and then I apply the exact same method that I did in my first example. So how does this work? So I start with the congruence having the largest modulus, so that's this last one. And I list out my list of positive integers that are congruent to 3 mod 11. Okay, so listing that out. So if I look at x is congruent to 3 mod 11, which x do I get? Well, 3, obviously, plus 11 is 14, and then 25, and then 36, and then 47, and 58, and 69, and 80, and so on, right? That's a bunch of them. Okay, so now I want to look at, I'm going to go to the next largest modulus, so I want to look at x mod 7. So I want to see what each of these things are mod 7. Well, 3 is still 3 mod 7, so that didn't change. 14 is 0 mod 7 because it's divisible by 7. 25 is 4 mod 7. 36 is 1 mod 7. 47 is 5 mod 7. And I'm done. Okay, at least at this step. What does this say? So this says that x is congruent to 47 mod 77. If that's confusing to you right now, you'll see in a second where this is coming from. I mean, you might already notice what's happening here, but you'll see exactly what it is that's happening here. So the fact that 47 is in the first line says that it solves the last congruence, and the fact that it is congruent to 5 mod 7 tells you that it solves the middle congruence. So it solves the bottom two congruences. Okay, so x is congruent to 47 mod 77 is the solution to x is congruent to 3 mod 11, and x is congruent to 5 mod 7. So now, what do? I make a list of positive integers that are congruent to 47 mod 77. Okay. So, what have I done here? I have essentially wrapped these bottom two congruences together, okay, into a single congruence now, which is 47 mod 77. That's what has happened here. So I list those out. So x is congruent to 47 mod 77. Okay, so I list out some of these things. I don't have to list out many, it turns out. So 47 is the first one, plus 77, that's 124, plus 77, that's 201. And so I want to compare this mod 5, and I'm looking for 4 here. Okay. And so mod 5, 45 or 47 is 2, and mod 5, 124 is 4. What does that say? This says that x equals 44 or x equals 124 solves all the congruences. Okay, and if you don't believe that, you can quickly verify that's the case. So 124 is congruent to 4 mod 5. It's congruent to 5 mod 7. And it's congruent to 3 mod 11. Okay. All right. So this is always going to work. Okay, this process is always going to work. But as you might imagine, this process here, our list of 3 congruences. One, we only had 3 congruences. We could have more. And secondly, the moduli could be a lot bigger, right? Here we just had 5, 7, and 11. We could have much, much bigger moduli, which would make this process a lot more annoying. So there is a way to turn this process into something that is actually more efficient, which we'll talk about when we're proving these facts related to the Chinese remainder theorem. So before moving on, I just wanted to point out what you're doing with this method is turning 3 congruences into 2 congruences. That's what you're doing at this step here. So these 2 congruences get wrapped up into this congruence. Okay. So what you're doing here is you are turning 3 congruences into 2 congruences, then doing the method from the previous example. Now, it's not worded in the best possible way because it turns out you're doing the method from the previous example to wrap those up into 2 congruences from the get-go. So really you're applying this method from the previous example twice. So you apply it once to the bottom 2 congruences that wraps it up into this congruence and the remaining one, and then you also use that same method again to be done. So what you're doing is you're doing this pairwise, and every time you take a pair of these congruences, they merge into one. Okay, so a pair of congruences merges into one and leaves you with one less congruence in your system of congruences, and then you just keep doing it. You collapse them one at a time, pairwise like this. The reason I keep harping on this is because what's really nice about the Chinese remainder theorem is this is essentially the proof of it. So yes, we use specific numbers here instead of talking about it generally, but actually there's pretty much no more insight that comes from this. The only thing I'll say here is that we are going to provide 2 different proofs of the existence part of the Chinese remainder theorem. And the reason for that is one of the proofs is going to be this very, very straightforward thing that we've done here. What is good about it is it's very intuitive. We literally pieced it together just going about this problem in kind of the only way you might naturally go about it. And then there's a second proof. And the second proof is a little less intuitive, but it's nicer in some ways. And so there's going to be a preliminary theorem that is essentially the Chinese remainder theorem for 2 congruences. We're going to prove that in 2 ways. And then we're going to state the Chinese remainder theorem and prove that in 2 ways. So the Chinese remainder theorem is the general result. Okay, so let's first state a special case. So first, we state a special case of the Chinese remainder theorem. Okay. So this is still called a theorem. Technically it doesn't have a name, it's just a number. If m and n are relatively prime, then the system of congruences X is congruent to A mod M, and X is congruent to B mod N, has a unique solution. mod m times n. Okay. So, this is an existence and uniqueness proof. Okay, so we have to show that such a thing exists, and then we have to show that it's unique. The uniqueness bit is very straightforward. I'm still going to write it out, but the uniqueness bit is pretty straightforward. So first I'm going to take care of existence. And in order to talk about existence, I'm actually going to go about this in two ways, like I said. So we prove existence in two different ways. So first proof. First proof is going to be how we did the examples. Okay. So since x is congruent to a mod m by assumption, then x is equal to a plus mt for some integer t. Okay. All right, but x is also congruent to b mod n. Okay. Thus, a plus mt is congruent to b mod n, i.e. mt is congruent to b minus a mod n. Okay. But the GCD of m and n is equal to 1. So let's look at this equation that I have written here. What would the GCD of m and n being 1 tell me about that equation? Well, here is where I said something yesterday when I was first introducing the Chinese remainder theorem. I said that this is very closely related to our solving of linear congruences. Okay, so our solving of linear congruences is related to this, and here's exactly how. Note, just because an x doesn't show up here, that doesn't mean anything. I have a linear congruence where I'm given a, b, m, and n. So t is the unknown here. But since the GCD of m and n is 1, by our big theorem that guarantees or tells us exactly how linear congruences might be solved and how many distinct solutions I have, modulo some integer, this says that it has a unique solution. So the fact that the GCD is 1 says it has a unique solution. As I mentioned, this was that corollary of that big theorem that I said was by far the most special, or by far the most important special case of that theorem. So how does this go? So this has a unique solution, say t naught mod n. Okay. Thus, x equals a plus m t naught is a solution to both congruences. So I'm defining this quantity. I claim that it is a solution to both congruences. To see that, x clearly is congruent to A mod M. Just by definition, it's A plus M T naught, so X minus A is a multiple of M, so clearly X congruent to A mod M. But the other thing to note is that, secondly, X being A plus M T naught is congruent to A plus M T naught is congruent to B minus A mod N. And A plus B minus A is just B. So X is congruent to A mod M, and it's congruent to B mod N. Okay. That's it. Now, if you unpack what it is that I've said here, you'll note that this is essentially the proof that, or rather, this was essentially, like, word for word, the method that I was actually using when I was listing out those solutions and then boxing in the common solutions to the two congruences. So this is exactly what I was doing when I was listing that out. Okay, so let's do the second proof of existence. Okay, so proof continued. So second proof of existence. Okay. So since the GCD of M and N is equal to 1, there exist integers U and V such that, you know where I'm going with this, MU plus NV is equal to 1. Right? Most powerful thing about the GCD, the thing we got from the extended Euclidean algorithm, is that the GCD of two numbers can be written as a linear combination of the two numbers. Right? So there exist integers, U and V, such that MU plus NV is equal to 1. Okay. Define X to be BMU plus A in V. Maybe I should use the definition colon here. Right. Okay. Note a couple of facts. MU is congruent to 0 mod M, and NV, which is 1 minus MU, is congruent to 1 mod M. Okay. Thus, X is congruent to B times 0 plus A times 1 mod M, but that's just A. So X is congruent to A mod M. Similarly, X is congruent to B mod N. So this is a much quicker way of going about it, right? This wasn't quite as intuitive and straightforward and constructive as the one we just did, the first proof. But this is very, very nice. One, because this proof is very quick, but two, this actually gives us another way of going about finding a solution to that system of congruences. So I'm going to do this in an example here in a second. But before I get into that, we got to finish this proof, so let's do uniqueness. Okay, so to show uniqueness, I want to show that if I have two solutions, then they have to be congruent mod m in, right? So mod m times n. So assume there exist two solutions, x sub 1 and x sub 2. Okay, thus, what does it mean if I have two solutions? So x sub 1 is congruent to a mod m, x sub 1 is congruent to b mod n, and also x sub 2 is congruent to a mod m, and x sub 2 is congruent to b mod n. Okay, so this means that x sub 1 and x sub 2, of course, are congruent mod m, and x sub 1 is congruent to x sub 2 mod n. Okay. Thus, by definition of congruence here, m divides x sub 1 minus x sub 2, and n divides x sub 1 minus x sub 2. Okay. Thus, x sub 1 minus x sub 2 is a multiple of both m and n. But GCD of m and n is 1. Thus, x sub 1 minus x sub 2 is a multiple of m times n, i.e. x sub 1 is congruent to x sub 2 mod mn. Right? Thus, you start out with any two solutions to your system of congruences, and you end up saying that those two things are actually congruent mod mn, so they are actually the same mod mn. Okay, so let's do a quick example before moving on to the actual statement of the Chinese remainder theorem. So quick example. So let's return to our congruences. X congruent to 2 mod 3, and x is congruent to 4 mod 5. But let's use that other method. So let's use the method from the second proof for existence. Okay. Whoop. Okay. So GCD of 3 and 5 is 1. I can quickly come up with a linear combination for these. No need for the Euclidean algorithm. This is easy enough. So 3 times 2 plus 5 times minus 1 gets it done. Thus, x is congruent to BMU plus ANV. Unpacking what those things are, this is 4 is B. That's 4 times M, so that's 4 times 3 times U, which is 2, plus A, which is 2, times N, which is 5, times V, which is minus 1. So this is 24 minus 10, that's 14, mod 15. That's exactly what we got doing it the other way. Okay. All right. And so this theorem that we've just proven is essentially all you need to prove the Chinese remainder theorem. The Chinese remainder theorem is the analogous statement when you have a list of congruences more than two. But as I mentioned before, what you do is you pick two of those, and using either method in the proof of this previous theorem, you combine those two congruences into one congruence. And when you do that, in your long list of congruences, you've essentially deleted one of them and put its data into some other congruence, right? So you've taken two and you've combined them. So you're losing out one congruence, but you're keeping same amount of info, and you just continue collapsing these, right? You just continue collapsing them until you solve the entire system. Okay, so that's how this works. So now it's time to actually state the Chinese remainder theorem. So theorem this is the Chinese remainder theorem. So assume that m sub 1, m sub 2, and so on, all the way up to m sub r are positive integers that are pairwise relatively prime. Right? The way to think about this is, i.e., GCD of m sub I and m sub j is equal to 1 for all I and j that differ. Okay. Then the system of congruences, which is x is congruent to a sub 1 mod m sub 1, x is congruent to a sub 2 mod m sub 2, and so on, all the way to x is congruent to a sub r mod m sub r. This system of congruences has a unique solution mod m sub 1 times m sub 2 times m sub 3 all the way to m sub r. Okay. So that's the statement of Chinese remainder theorem. Let's go through proof of this. So proof, again, we prove existence in two different ways. Okay. So first proof is the following. So we're not going to care about an efficient way of doing this. We're just going to proceed starting at the top, going toward the bottom. We don't care about ordering the moduli or anything. So we're just going to start at the top, make our way toward the bottom. So pair up the first two equations and use the previous theorem. That is the Chinese remainder theorem special case when you only have two congruences. So use the previous theorem to find a solution. Well, a solution to those two, we can rewrite that as x is congruent to b sub 1 mod m sub 1 times m sub 2. Of course, we can do this because m sub 1 and m sub 2 have GCD 1, right? They're relatively prime because they're pairwise relatively prime. So each of these m's, m sub i's, is relatively prime to any other one in the list. Okay. So let's say we found a solution in that way. So the next pair this congruence. When I say this congruence, I mean this one, right? This new congruence I've gotten. Pair this congruence with the third congruence. X is congruent to a sub 3 mod m sub 3 to get a solution to the first three congruences. And again, because we're combining one congruence here with one more congruence that's our third congruence, again, it's just two congruences, so the previous theorem applies, and the result of solving those two congruences yields a solution that solves the first three congruences in this list. And we call that x is congruent to, say, b sub 2 mod m sub 1, m sub 2 times m sub 3. Right. Continue until we find x is congruent to b sub r minus 1 mod m sub 1, m sub 2, all the way up to m sub r. So do this thing r times, and we're done. That's exactly the process I described in words when I said, take this method we have of dealing with two congruences at a time and just keep collapsing that list of congruences, one congruence at a time. Eventually, the thing that you get solves everything, right? So maybe I should say that explicitly. B sub r minus 1 solves all of the congruences. Okay. All right. So that's the first proof of existence. As before, we have a second proof, and it actually is very similar in spirit. So proof, second proof of existence. So what is this? So the second proof of existence starts out by saying, let M be the product of all the M sub i's. Okay, and let N sub I be M divided by M sub I. Okay. So one way of thinking about this, of course, is that it's the product of all the m's except m sub I is not included. Okay. So it's the product of every all the m's except m sub I. Okay. Now claim that the GCD of n sub I and m sub I is equal to 1. So now I have a subproof of this claim. So suppose not, and let P be a prime that divides GCD of n sub I and m sub I. Okay. Well, since it divides the GCD, it has to divide all the n sub i's. P divides n sub I. Okay. Thus, P divides n sub I, with n sub I defined in this way. Then P divides m sub j for some j not equal to I. Well, it's because P divides a product. The only thing not in that product is m sub I. All the m sub j's are. So it divides one of those m sub j's, right? You have a prime divisor dividing a product. It divides one thing in the product, right? It divides at least one of those things. Okay. But I said that P divides the GCD of n sub I and m sub I, so P divides m sub I as well. That's because it divides this GCD. Okay. Thus, P divides the GCD of m sub I, m sub j, and I and j are not equal. These things are pairwise relatively prime. So if I have a prime dividing the GCD of n sub I and m sub I, turns out it actually divides the GCD of m sub I and m sub j. Okay, but that GCD has to be 1. And P being a prime can't divide 1. This is a contradiction. And thus this claim is verified. So the GCD of n sub I, m sub I is 1. Okay. Thus, coming directly from this claim, what does this allow me to do? Well, there exist some u sub I integers such that n sub I, u sub I is congruent to 1 mod m sub I. Okay. Why? This is simply a statement that follows. It's one of those corollaries from the big theorem 6.18. So theorem 6.18 is the theorem that tells you about solving linear congruences. Okay, so we have this fact. I know that my n's and u's look very similar, and I apologize for that. I try my best to make that not be this way. Anyway, for each I, we get u sub I that is a unique inverse to n sub I mod m sub I. Okay, so that's what this statement is. These are multiplicative inverses for each n sub I. So let x be equal to a sub 1, n sub 1, u sub 1, and so on, all the way up to a sub r, n sub r, u sub r. Okay. So each term is 0 mod m sub I except for the ith term a sub I, n sub I, u sub I, i.e. x is congruent to a sub I, n sub I, u sub I mod m sub I, but this n sub I times u sub I is congruent to 1 mod m sub I, so this is congruent to a sub I mod m sub I. And so, by construction, x solves my list of congruences. And that's it. So that was a little bit tricky. Technically, I need to prove uniqueness, so uniqueness, I'm just going to say this is similar to the case with two congruences. If you want to have a look at that, this is on page 140. I'm not going to go through that. And so, very similar. You just have a product of m sub i's now, but it's the same deal. Okay. So, this method of computing here, maybe I should really circle this. This gives us a very slick way of coming up with solutions to problems involving solving some system of congruences. Let's do a quick application of this, and then we will be done. Okay. So here's a quick example. So let's revisit our original problem. So the original problem had three congruences. X is congruent to 2 mod 3. X is congruent to 3 mod 5. And X is congruent to 2 mod 7. Okay. So let's use the second proof method. Since the first proof method is straightforward and we've already done an example of that. Okay. All right. So what is this method? Let me just remind you. This is the form that X takes. This sum. Okay. So, using this, n sub 1 is 35. Right? Remember, n sub 1 is the product of the m's, except it leaves out, so in this case it leaves out the first one. So it is, instead of being 3 times 5 times 7, it's just 5 times 7. N sub 2 leaves out 5, so it's 3 times 7, so it's 21. N sub 3 leaves out 7, so it's 3 times 5, it's 15. Okay. So then I solve 35 times u sub 1 is congruent to 1 mod 3 to get u sub 1 is 2. And then I solve 21 u sub 1, or sorry, u sub 2 is congruent to 1 mod 5 to get u sub 2 is equal to 1. And lastly, I solve 15 times u sub 3 is congruent to 1 mod 7 to get u sub 3 is equal to 1. Thus, X equals, writing this out, this is a sub 1, n sub 1, u sub 1 plus a sub 2, n sub 2, u sub 2 plus a sub 3, n sub 3, u sub 3. Writing this out, this is 2 times 35 times u sub 1 is 2 plus 3 times n sub 2 is 21 times u sub 2 is 1 plus a sub 3 is 2 times 15 times 1. So putting it all together, this is 233 but I look at that mod 3 times 5 times 7, which is 105. So that is congruent to 23 mod 105. Okay. So let's just check. If I look at this, does it solve all three congruences? So 23, if I divide by 3, its remainder is 2. If I divide by 5, its remainder is 3. If I divide by 7, its remainder is 2. Nice. Very nice. Okay. So, one more example of how the Chinese remainder theorem gives you a new way of looking at one of the congruences we looked at a couple sections ago. So, example, Chinese remainder theorem also gives new insight into other sorts of congruences. So, for instance, let's say that we have x squared is congruent to 1 mod 275. Okay, so here I have big modulus. All right. So then the question is there a way of going backwards in a sense by the Chinese remainder theorem and splitting this apart using its prime factorization to get, instead of having a single congruence, I would get a list of congruences and then I would solve that system. Now, the first question naturally you might ask is, wait, why would you ever want to start with a single congruence and turn that into a system of congruences? That sounds like that wouldn't help at all. Sometimes that's actually easier to deal with. Because remember, you're going to be splitting this up, so depending on the factorization in question, the moduluses are going to be a lot smaller, and so the congruences you get as a result of that might be a lot nicer to handle. So note 275 is 5 squared times 11. That's its prime factorization. So, i.e., this is equivalent to the system x squared is congruent to 1 mod 5 squared, which is 25, and x squared is congruent to 1 mod 11. Okay. So the first one, this has solutions. X is congruent to 1 or minus 1, which is in this case 1 or 24 mod 25. This one has solutions. X is congruent to 1 or 10 mod 11. And so now I look at how I can actually combine these, right? So there's 4 ways of doing this. So I have to keep track of each of these. So I have x is congruent to 1 mod 25, and x is congruent to 1 mod 11. Combining those, I get x is congruent to 1 mod 275. Okay. And then secondly, I get x is congruent to 1 mod 25. X is congruent to 10 mod 11. That combines to give me x is congruent to 76 mod 275. Okay. So that's how that combines. Next, x is congruent to 24 mod 25, and x congruent to 1 mod 11. So that gives me x is congruent to 199 mod 275. For each of these, you can use the special case, the Chinese remainder theorem, so the theorem that I stated before that. And then lastly, x congruent to 24 mod 25, and x is congruent to 10 mod 11. So how does this combine? You get x is congruent to 274 mod 275. Okay. Thus, the solutions are 176, 199, and 274 mod 275. Oh, I'm off screen. There we go. Just rewriting that. Okay. So that's another way that the Chinese remainder theorem can be applied in a way that doesn't immediately look like it has anything to do with it. So this is a way of starting with a single congruence and breaking it into a system of congruences to solve. Sometimes this is actually easier to deal with. Okay, so rather than go ahead and start chapter 7, I'll just keep it nice and contained, beginning with a new lecture. So I think that's all I'll say today. So Chinese remainder theorem stuff is finished, and we'll do, starting on Friday, we'll start with chapter 7, which is cipher stuff. So I will go through a couple of examples of some very simple encryption ideas. And so I'm not going to, as is mentioned in the textbook, there's some things about encryption that are not discussed because they don't really involve number theory. So we'll basically be focusing on the stuff that purely relates to number theory. So anyway, we'll start that stuff tomorrow. So I will see you all then.